Hi guys, this is a Calc video 5-12. See your email for this notes page, and this is to be watched Wednesday, January 18th, and for the homework also see the email. Whenever you are given, so we're just basically continuing yesterday. Whenever you are given a function that represents the rate of change or the derivative of another function, write down the following information. Okay, so displacement, so it'll be called displacement when you're dealing with particle motion, like velocity, acceleration, all that. It'll be called net change if you're dealing with something else. But let's turn that f prime to a v. And then same thing over here. So total distance, you're usually going to be given velocity for that. So turn that to a v. Okay, so net change or displacement is given by the integral from a to b of the velocity function, or the first derivative if you're not dealing with displacement, if you're just dealing with the net change of something that's changing. You'll see that in a moment. Total distance will be the integral from a to b of the absolute value of velocity. And then you could always find an antiderivative. If you know the derivative function, you could always find the antiderivative of it with this formula here. Okay, so there's that. Now, here's a problem. Suppose a population of wild badgers is increasing at a rate of 100 plus t to the 2/3 badgers per year, where t corresponds to the number of years after 2008. So 2008 is year 0. Assuming the rate does not change, okay, so this always will give us the rate. Okay, the rate function won't change. Assuming the rate does not change, by how much will the badger population increase from 2010 to 2012? Guys, they're asking for the net change. Okay, by how much will the badger population increase? Okay, so they want the net change in the badger population. So how do you find net change? It's this here. Now first, I would give this a name. All right, so if we let P be the population of badgers, that would be P prime. Okay, so we know they're giving us that P prime of T equals 100 plus T to the 2/3. And this is the rate of change of the badgers per year. If I want to find the net change in badgers on a certain interval, I'm just going to have to use this net change formula. But let's figure out, like, okay, so at 2008, that is t equals 0. They want from 2010 to 2012. So what are those times? Okay, so 2010, that'll be t equals 2, right? Yeah. And then 2012, that'll be t equals 4. All right, so I want the net change over that interval. So net change in badger population is given by this integral. Okay, the integral from 2 to 4 of P prime dt. All right, and then plug that into your calculator. I already did it, so I'll tell you the answer to save us time. You should get 204.1427 badgers. Okay, so the net change, maybe some badgers died, maybe some badgers were born, but all in all, the net change over this interval of time was this many badgers. Okay, there's this many more badgers at the end of that time interval than there were at the beginning of it. Okay, so there's that. Now, let's do this example on the next page. Okay. The graph of the velocity of a particle moving on the y-axis is given. Okay, it's this graph here. The particle starts at y equals 3 when t equals 0. Okay, so I'm going to translate this here. So I'll call y of t, the position function, so we'll say y of 0 equals 3. All right, I'm letting y of t, y of a certain time, be the position on the y-axis. During what intervals of time is the acceleration of the particle positive? All right, well, you need to know, I would write this to myself, so I want to know when v prime is positive, and then we've got to explain. All right, so let's do that first. So, A. Okay, well, this is the velocity function, and they want to know when when the acceleration is positive. So when is the derivative of this positive? Well, it would not hurt to have like Susan's table next to you, or the physics version of Susan's table. And if anything I say during this process does not make sense to you guys, you should look back at those tables and try to think it through from there. Okay, so when is the derivative of this? Okay, so the acceleration is the derivative of this. So when is the derivative of this positive? It's going to be, let me see, for these times. So t for the times 0 to 2 union 6 to 7. And if I were you, I would pause it right here and try to think about why. Okay, so that'd be a good exercise. I'm going to just jump to the reason though. And I'm going to say because v of t is increasing. All right. Guys, notice they're giving me the velocity graph, so my explanation has to deal with the velocity graph. If you said because this is where the acceleration is positive, that would be redundant. The reason you know that the acceleration is positive is because that's where this graph is increasing. And if this graph is increasing, then its derivative is positive. Okay, now for part B. What is the acceleration of the particle at t equals 4? All right, is the particle speeding up or slowing down? Explain. All right, well, let's find, okay, so t equals 4 is here. And since this is linear, I can find the acceleration because the acceleration would be the rate of change here. So, so I want, all right, so the acceleration, let's write this down. The acceleration at 4 equals v prime of 4 equals, you could just count slope, rise over run. So down 1, right 1 equals -1. All right, so that's the acceleration there. Now, we're still on part B. They're asking, is the particle speeding up or slowing down? Explain. Well, if you remember from the physics version of Susan's table, a particle, to decide if it's speeding up or slowing down, you have to look at the acceleration with the velocity, and you look at their sign pairs. So we know that the acceleration is negative. If the velocity is also negative, then the particle will be speeding up because they'll have the acceleration and velocity will have the same signs. But if the velocity is positive, then it'll be slowing down because the acceleration and velocity will have opposite signs. So let me find the velocity. So v of 4, this is the velocity graph. Okay, so I go to 4 and then the output here is +1. All right, and then so the verdict is slowing down. And I'll say because the acceleration at 4 is less than 0 and the velocity at 4 is greater than 0. All right, so they have opposite signs, which means that the particle is slowing down. C, set up an integral to find the displacement of the particle in the interval 0 to 7, and then use the graph above to evaluate the integral. Okay, so displacement, all right, this is the front of this. The displacement is given by this integral here. All right, so for part C, I need the integral from 0 to 7 of velocity. All right, and when I look at this, I see like 3 shapes. I see this triangle, which will have a negative area. And then I see this triangle, which will have a negative area. And then I see this trapezoid. And if you ever like forget the formula of a trapezoid, you know, you could split that up into rectangles and triangles. So I'm going to split this integral up into 3 integrals. So I'll do the integral from 0 to 1 under the velocity graph, plus the integral from 1 to 5. This is called additivity, the way I'm splitting this up, plus the integral from 5 to 7. All right, and then I just find, you know, the areas of these. Now, to go real fast, guys, I'm just gonna tell you what it is. So this, for this triangle here, I end up with an area of 1, but since it's below the x-axis, that's going to be a negative area. Plus, this trapezoid, the area of that trapezoid is 5, and it's positive because it's above the x-axis. And then plus the area of this last triangle, it's negative because it's below the x-axis, and it's a -1. Okay, so we end up with 3. Okay, so what does that mean? It means that at the end of that interval, from 0 to 7, we are this far from our initial position. All right, that's what displacement means. Okay, now D. Find where the particle is at t equals 7. Okay, so find where the particle is at t equals 7. All right, so I want y of 7. All right. Well, guys, if I'm calling y the position function, then the velocity function is the first derivative of that. Okay, and then maybe I should say this. Note, if y of t is position, then v of t equals y prime of t. Okay, so that's a good observation, because what I can use, so I'm trying to think, I'm trying to get backwards. Okay, I've got the derivative of the position because that's velocity, and I'm trying to think backwards. Well, this antiderivative formula, guys, will always help you get backwards. Okay, so right there. So as long as you have the initial position, then you could use this derivative, or this antiderivative formula. So I've got y of t is equal to y of 0 plus the integral from 0 to t of v of x dx. Okay? And I want y of 7. Well, y of 0, they told me at the beginning that was 3, plus from 0 to 7 v of x dx. Guys, I already found this. All right, this here, that was our answer to part C. So this is 3 plus 3 equals 6. All right, so y of 7. So that's the position. So we are on the y-axis and we are at position 6. That's the y-coordinate of the of our point, which is on the y-axis. Now finally, E. Set up an integral expression to find the average velocity of the particle over this interval. And guys, when I was doing this earlier, oh shoot, I'm not even indicating units of measure, am I? Darn. Yeah, I wasn't indicating any units of measure, which is not good. I'll go back through in a minute. Okay, so average velocity. Guys, whenever you hear like the average, so we've got this velocity function right here. And we want the average velocity, so we want the average value of this function. So you have to know this formula. Okay, so this is part E. Okay, if you want the average value of a function, it is given by this formula, 1 over b minus a, the integral from a to b of the function. Well, they want the average velocity over the interval 0 to 7. So the average velocity is going to be 1 over 7 minus 0, integral from 0 to 7. Oh, I'm switching. You could use x or t, it doesn't matter. All right. And so this is 1/7. And then that, guys, this keeps coming back over and over. We found this in part C. That's 3. So 3/7. Okay, now let me go back through. I need units of measure. Okay, so what are the units on velocity? Meters per second. Okay, because that's the average velocity. So meters per second. Now, this was position. Okay, so that should just be meters. Okay, 6 meters, I guess, above the origin. Okay, so that was D. Part C, this is displacement. So we're 3 meters from our initial position. And then part B, this should have been meters per second squared, or meters per second. And then this is just meters per second because it's velocity. Yeah, so there's that. Okay, guys, shorter than yesterday, and I will see you soon. Bye-bye.